Okay, so in this video, we're finally going to get to threats to statistical validity and how to spot them. So in the earlier videos, we talked about how there are a lot of false positive findings, or at least we need to be worried that there might be, and that this is likely due to things like p-hacking, harking, and file drawering. So today we'll talk about how do we avoid making these false positive and also false negative errors, and how do we spot these errors? So how do we evaluate the statistical conclusion validity of other people's claims? So we're going to still be talking in the framework of NHST, where we use p-values. And as we learned, p-values are a way to ensure error control, that when the null hypothesis is true, we control our type 1 error or false positive error rate with alpha. When the null hypothesis is false and there is an effect, then we try to reduce the chances of a false negative error. So we'll talk about how do we control false positive errors, how do we control false negative errors. So for false positive errors, as I just mentioned, we use alpha to control the risk we're willing to take of making a false positive error when the null hypothesis is true. So we pick alpha to be 5% in psychology, which is saying that when the null hypothesis is true, we should fail to reject the null. We should conclude we can't see anything there. We're willing to accept that 5% of the time we're going to accidentally think there's something there. So we're willing to accept an alpha percent or 5% chance of a false positive error when the null is true. So if we want to reduce the chance of a false positive error, we can just lower our alpha. So we could say I'm only willing to accept a 1% chance or a 0.5% chance of a false positive error. And some of us have advocated for lowering alpha. And you could decide that you're going to lower alpha if there's really a lot at stake and a false positive would be a really bad thing. So you could also decide on a case-by-case basis what level of false positive error rate you're willing to tolerate. The other way to make sure that you control false positive errors, and this is absolutely necessary in NHST if you want error control, is to follow the rules of NHST. So that is, in order for you to have this guarantee that the chances of a false positive when the null is true are no more than alpha, then you have to make sure that you make your p-value accurate. And to do that, you have to make sure that you don't choose your statistical analysis after looking at the data. So all these things that we talked about, p-hacking, harking, file drawing, all have to do with making a decision about how to analyze or interpret your data after you've already seen some results. And NHST does not allow that. If you want p-values to have their meaning and you want error control, you want your false positive error rate to be controlled at alpha, then you have to follow the rules of NHST. You have to pick your analysis, how you're going to analyze your data, what p-value you're going to calculate ahead of time before seeing your data. Once you see your data, you can't go back and change that. If you do, that p-value is no longer going to have that error control property. Sometimes, of course, you should abandon NHST and say, I made a silly mistake, I should have analyzed my data a different way, but now you're giving up that error control promise. So if you do all these things, you have an alpha, you stick to the rules of NHST, then you can have that reassurance that if the null hypothesis is true, there's only an alpha percent chance in the long run that you would get a false positive. Even then, that doesn't guarantee there won't be a lot of false positives. So we talked before about how the type 1 error rate, the false positive rate, which is fixed at alpha, is the percentage of false positives in the left column when the null hypothesis is true. But what we actually care more about is when we get a significant result, when we're in the bottom row, what are the chances that it's a false positive? We care more about this because we know when we're in the bottom row. So this is a meaningful percentage. We don't know when we're in the left column. So knowing that there's only a 5% chance of a false positive in the left column, that's nice, that helps us sleep at night, but it doesn't help us know what percentage of our significant results are false positives. That's this percentage, the bottom row percentage. And that's known as the false discovery rate, the percentage of false positives among all the positive or significant results. And that we can't control. So we always have to worry that there might be a lot of false positives when defined this way, even if we follow the rules of NHST. So in other words, there are two kinds of false positives. There's type 1 error rates, the alpha percentage, which is the percentage of false positives in the left column. We can control that by setting alpha and following the rules of NHST. And then there's the false discovery rate, which is the percentage of false positives among all significant results in that bottom row. We can't totally control that. There are ways that we can try to reduce it. We can check what it might be by doing replication studies, for example. I won't get into how that works, but there are ways to try to estimate it and make sure it's not out of control. But there's no guaranteed formula for making sure that that percentage is low. Okay, so that's false positives. What about false negatives? How do we avoid taking too high of a risk of making a false negative error. So we can reduce the chances of false negatives in a few different ways. One is by just studying really large effects. If the effect you're studying is very, very large, you're less likely to miss it, right? So if I'm interested, for example, in sex differences in height, I am pretty likely to be able to detect that men on average are taller than women. That's a really big effect and quite hard to miss. But obviously that's not very useful because I want to study the research question and the effect I want to study. I can't just ditch it and choose a research question with a bigger effect. Often I'm just inherently interested in the question and the effect regardless of its size. So other options, use really reliable measures. That's going to boost the signal that there is to detect relative to the noise. So reliability reduces random error, reduces noise. And the more we can reduce noise, the more the signal, better chance the signal is going to pop out. Another option, but one that I don't recommend, is to increase alpha. So I just talked about how you can reduce your chances of a false positive by decreasing alpha from 5% to 1% or 0.5%. If you want to decrease the chances of a false negative, you don't want to miss anything, then you increase your alpha. You say, oh, I'm willing to tolerate a 10 or 20% chance of a false positive, but then I'm more sure that I won't make a false negative. So there's a trade-off there. You're not going to get away with that very easily. There might be some scenarios where the stakes are really high. We don't want to miss something if it's there. If it's a false positive that doesn't hurt anybody, but a false negative could really hurt people, then we might say, okay, raise alpha, take a bigger chance of a false positive, but let's just make sure we don't miss anything that's actually there. That doesn't often fly, especially in basic research, but in applied context, it might sometimes be justified. The most obvious way and the most useful way to reduce your chances of a false negative is just to collect a lot of data. So if you collect a lot of data, you increase your sample size, you collect more observations, you're more likely to detect something that's really there, right? The more evidence you have, the more likely that if there's something there, you're going to see it. So let's formalize that a little bit more. So the chances of a false negative is, now we're talking about the right column, the world where there really is something to detect. You want to make sure you don't miss it. So the chances of missing it when there really is something there is your false negative error rate, or beta. And so the inverse of that, the rest of the percentage, is the chances of detecting an effect when there really is one there. And we call that statistical power. It's just 1 minus beta. So if our chances of a false negative are 20%, then our chances of detecting something that's really there, our statistical power, is 80%. So how do we increase statistical power? Well, those 4 ways I just mentioned are all ways to increase statistical power. They reduce the chances of a false negative. They increase the chances of detecting an effect that's really there. So let's dig in a little bit more to the sample size issue, because this is the most common way and the most effective way to increase your statistical power or reduce your chances of a false negative. So why does increasing sample size, collecting more data, more observations, increase statistical power? Let me illustrate this by going back to a concept we introduced a little while ago, the sampling distribution. So this is, if you ran your study over and over again, what would the distribution of results look like? So when you have a small sample size, few observations, you could get really wacky, extreme results. So imagine I'm going to do a study with a sample size of just 10, and my study is flipping a coin to see if it comes up heads or tails. The null hypothesis, there's no difference in the probability of heads or tails, 0 effect. Is going to come out some of the time. A lot of the time when I do my study with a sample size of 10 observations, I'm going to get 5 heads and 5 tails, but not always. Sometimes I'm going to get 6 heads or 4 heads. Sometimes I'll even get 7 heads or 8 heads, and once in a while I'll get 9 heads. With a small sample size, like only 10 observations, it's going to happen quite often that I get 8 heads or only 2 heads. Now imagine if I increase my sample size a lot. Let's say now instead of 10 coin flips, 10 observations in my study, I'm going to get 1,000 observations in each study. And then I'm going to run that study over and over again. Now the sampling distribution is much narrower. So if I'm going to run 1,000 observations per study, then the chances that I'm going to get something very far from 0, very far from 50-50 in the case of flipping a coin, get much, much smaller, right? The chances of getting 800 heads out of 1,000, if it's a fair coin, if the null hypothesis is true and the probability of heads and tails are equal, I'm not going to almost ever get 800 heads out of 1,000, even though when I'm only flipping 10 times, I will get 8 out of 10 quite often. So that's a way to think about the fact that with a small sample size, you get fluky extreme results more often. The sampling distribution is wider. Okay, Now, what does that have to do with statistical power? Now, when we're talking about statistical power, we're talking about the right column world where there really is an effect there. The null is false. We're actually not drawing our study results from the null distribution. We're drawing our study results from some other distribution of the actual effect that is not zero. So you introduce an actual distribution that's not centered around zero. This is where our study results are actually coming from. But we're going to be comparing our actual study results to the null distribution to see if we can reject the null. So we want the result we get from our actual distribution to be as far away as possible from zero. When our distributions are wide, then a lot of the results we'll get from our actual distribution will overlap quite a bit with the null distribution. However, if we increase our sample size and we shrink the width of each of these distributions, now when we draw from our actual distribution, we're going to get results that are much further away from the null distribution much more reliably, even though the averages of those two distributions haven't changed. The true effect in the actual distribution is still the same as in the top example, but now that distribution has shrunk in width, and so we're going to reliably get more results closer to the actual effect size in the actual distribution and further away from the null distribution. So you can think of this as how much overlap is there between the null distribution and the actual distribution. And with a larger sample size, there's less and less overlap, which means we're going to be able to reject the null hypothesis more often. We're going to get a result that's far away in the tail of the null distribution with a small p-value and reject the null. So this is why increasing your sample size helps your statistical power. So increasing sample size reduces the random error. You get less fluky results. You get more reliable results. This is the same principle of aggregation that we talked about when we talked about reliability. You increase reliability by just collecting more observations, aggregating them together. You cancel out random error. So you get closer and closer in on a particular estimate. If that particular estimate is not zero, because the null is false, there really is an effect there, then you're going to narrow in on the true effect size. And so when the null is false, when that true effect size is not zero, increasing sample size creates less overlap between the null distribution and the actual alternative distribution that you're actually drawing from, which makes it easier to reject the null. This is especially important when your true effect, your non-zero effect, is close to zero. So when the actual distribution is close to zero, you have to make it really quite narrow for it not to overlap very much with the null distribution. So you need quite a large sample size to be able to make them overlap less, to give you a good chance of rejecting the null. When the null is true, when you're in that left world, statistical power is now irrelevant, but you might be concerned, wait, am I doing anything to my chances of a false positive if the null is true? Because we never know if we're in the left world or the right world. But you don't have to worry. When the null is true, increasing your sample size doesn't change your chances of a false positive. It's still alpha% when the null is true, or 5% when alpha is 0.05. So increasing your sample size is always a good thing from a statistical error point of view. It always reduces your chances of a false negative error, and your chances of a false positive error stay the same. So larger sample sizes are always better, except that they're harder and more expensive to collect. So putting aside the costs of actually collecting the data, from the standpoint of statistical validity, larger sample sizes are always better. This is also true in other frameworks besides NHST, even if you're not in the NHST framework. Okay, so to summarize, we've talked about things that we want to do to avoid false positives and avoid false negatives. So I'm just going to summarize the most important points here. Things to remember to do or not do if you want to make sure that you have good statistical conclusion validity. And these are also good things to look out for when evaluating other people's claims to make sure that those claims have good statistical conclusion validity. So if they get a positive result, you want to look for red flags and things that cause false positives. So things that cause false positives are things like hypothesizing after the results are known. So do you know for sure that this was their key research question going into the study? They can help with that by documenting that ahead of time. P-hacking, did they run multiple analyses, or could they have? Maybe you can't tell, but they ran one really funny analysis where you have to, drop these outliers and control for this and transform that variable. That should be a red flag that maybe that wasn't always the plan and they had to do that to get a significant result. File drawing, do you know about the negative results? Would you have known about it if it had come out negative? And there are ways to guarantee that. Authors can make a commitment to publishing the results either way through things like special mechanisms called registered reports, where an author commits to publishing the result however it comes out. And then I don't have time to get into why this is, but I'd be happy to chat about it with any of you. But it turns out that if the p-value associated with the result is close to 0.05, like it's 0.04, 0.03, 0.06, anywhere in that range of like just below 0.05 or at or just above, but they're still interpreting it as a positive finding, that's a reason to be a little bit more skeptical. And if you're seeing a lot of p-values and they're always kind of in the 0.02, 0.03, 0.04 range, they're never getting really close to 0, 0.001, 0.005, 0.008, that should be a reason for skepticism. And I'd be happy to discuss why, but if across many studies, if there really is an effect there, you should be seeing lots of p-values below 0.01, not just 0.04, 0.03. Okay, so those are red flags about false positives. What about false negatives? The main thing that causes a false negative is a small sample size. So small sample size can mean different things in different contexts. It depends on the types of effects you're studying. And sample size could be the number of participants you have in your study, but it could also just be the number of observations or trials that each is collected on each participant. So this really has to be evaluated in a context-specific way, but a small number of observations can be problematic for false negative reasons. Another really important thing to look out for false negatives is if authors or researchers interpret a non-significant result where they should just say, we don't know what happened, we can't reject the null, but we can't say that the null is true. If they interpret that as evidence that there is nothing going on, they say, oh, there's no difference between groups, we can be confident about that, or we conclude that this manipulation had no effect, or that there's no correlation, that should be a red flag if all they're relying on is NHST or a non-significant p-value. So another way to say this is that absence of evidence is not evidence of absence. So if I did a study and I didn't get a significant result, I failed to reject the null, but that doesn't mean that I have evidence that the null is true. So remember when we talked about these 3 possible conclusions in NHST, we said that actually the second one is never an acceptable conclusion in NHST. You'd have to go beyond NHST, beyond p-values, to actually get a statistical measure of how likely is the null hypothesis to be true, or how confident can I be in accepting the null. NHST can't do that for you. So look out for that and make sure not to slide into that kind of error. Okay, so those are kind of the main threats to false positive errors and false negative errors. I would summarize the false positive errors as basically violations of one really important rule of NHST, which is that you cannot choose your statistical analysis after looking at the data. So one of the rules of NHST, in order to maintain your false positive error rate under control, is that you have to plan how you're going to analyze your data ahead of time, and you can't change that analysis after looking at your data. If you do, you're no longer in the world of NHST. That's okay. Not everything has to be in NHST, but you can't have the assurance of error control anymore. You are now increasing your chances of a false positive. There's also a bunch of other general threats to statistical validity that I didn't have time to get into. I just talked about the biggest threats that could cause false positives or false negatives, but there's a lot of other ways that statistical analyses can go wrong and therefore lead to invalid statistical conclusions. Hopefully you've learned about some of these in your other classes. Since this isn't a statistics class, we won't get into them, but I just want to mention a few of them, like if you have outliers, those could be driving the effect and you don't realize it. Or if you have floor or ceiling effects, so everybody's giving the same answer towards the bottom of your scale or towards the top of your scale, and that hides some variance that would actually be there if you expanded the scale. Or if your data are violating some of the assumptions of your statistical tests. So many statistical tests have many assumptions built in, like assumptions that the variables are normally distributed, or other kinds of assumptions. If you violate those assumptions, then your statistical conclusions may lack validity. So here's a few tips I'll leave you with when evaluating statistical conclusion validity. First of all, if the researchers are using NHST and p-values, then they should follow the rules of NHST in order to ensure error control and that their p-values have meaning. But even then, I would make sure that you don't treat the p-value as a direct pipeline to truth. The p-value tells you one very specific probability under the assumption that the null hypothesis is true. That's not the same thing as knowing what the truth is about your theoretical claim or your hypothesis. We have to use a lot of critical thinking and reasoning to evaluate whether we have good reason to conclude that there's an effect there or not. We should not just rely on the p-value. Another really important suggestion is to plot the data. Always look at the raw data, visualize the raw data. If the researchers are not showing you what the data actually look like, then you should be a little bit more skeptical. And ideally, they should make the data available to you so that you can check for yourself. But this graph shows that you can get the exact same correlation with a lot of different patterns of underlying data. So all 4 of these plots have the exact same correlation between the X and Y variable. But when you look at the underlying data, you see that in some cases it's driven by an outlier, in some cases it's driven by a nonlinear effect, etc. This is called Anscombe's quartet if you want to Google it. Another recommendation is to ask for replications or try to replicate something yourself. If the effect is real, if it's a true positive, then it should show up most of the time that you attempt to replicate it. And the best way to be sure about a positive finding is to make sure that you can get it over and over again. Now that just ensures statistical conclusion of validity, that it's not a false positive. Doesn't mean that you're interpreting it correctly, that you have all the other kinds of validities. But for ruling out the threat of a false positive, replication is a really good way to go. And then finally, use common sense. So just because we're now in the world of statistics doesn't mean we should throw common sense out the window. So in plotting the data and thinking beyond the p-value, really what I'm appealing to is to not turn off that critical thinking part of your brain just because we have statistics. Statistics are a tool, but they don't replace critical thinking and reasoning.